Hello, and welcome to our webinar on QC Ware Forge. Our team has just released a new version of Forge, and we're excited to share several new features, which we will demonstrate over the next 30 minutes or so. As we are presenting, please use the Q&A function to submit questions, and we will be happy to address them at the end of the presentation. So we initially released Forge back in September of 2019, and the new version just went live just a few weeks ago. Anyone can navigate to forge.qcware.com or simply search for QC Ware Forge and sign up for a free 30-day trial today. There are two types of users we're targeting with this new version. One is the quantum computing expert that wants to get results as quickly as possible. For the experts, the new capabilities we're introducing are editing quantum circuits, GPU-accelerated simulation of circuits, and importing existing circuits from other languages. The second type of user we are targeting are users that are new to the field of quantum computing and wish to use quantum algorithms to see what they're capable of, what kind of input they require, and what kind of output they can produce. For these users, we offer turnkey implementations in binary optimization, unique algorithms in quantum machine learning, and a ready-to-use Python notebook environment. In the next few minutes, I will call on the principal researchers in our team to specifically showcase the algorithms we offer in binary optimization, which include performance-boosting techniques for quantum annealing and QAOA. And we will also showcase complete, new, and groundbreaking capability in quantum machine learning for classification, regression, and clustering. QC Ware Forge is all about using quantum computing algorithms that you either build on your own if you're an expert, or utilizing some of our very unique implementations. Algorithms are what we do best, and that is the unique element about QC Ware Forge. However, we wanted to make it easy to execute these algorithms on either simulators or real hardware. That is why we're bundling hardware access in the same product. What we're offering are three types of hardware backends: annealers, specifically the D-Wave quantum annealer; circuit backends through Amazon Braket, specifically IonQ and Rigetti; and classical hardware to power simulation needs. So now let's go see QC Ware Forge. You can easily sign up for the service, and once you verify your email, you can come back to forge.qcware.com and log in. Once you're in, you can see a number of options on the navigation panel on the left. There is a Getting Started page that walks you through the basics of managing your account, your API key, getting started with notebooks, and more. Under API, you can find the API key that is needed to run any notebook and some of your recent API calls. Under Backends, you can see the currently supported backends and their status. Notice that the Amazon Braket backends are still not available, as Braket is still in private beta. By clicking on Jupyter Notebooks, you can jump straight into your Jupyter Notebooks sandbox. This will allow you to call any of our APIs and edit or execute algorithms on simulators and hardware. Once you're in, you can find the Getting Started with Forge notebook that walks you through the basics. Here, we're solving a simple binary optimization problem. We will import the QC Ware library, add our API key from over here, define the specific Q matrix that we want to solve for, and then we can run on a classical simulator and get the optimization solution, or run on D-Wave hardware. You can also explore some other notebooks that we have available on other topics. So with that, I would like to invite Rob to talk in more detail about some of our new capabilities on circuit editing and simulation.
Good afternoon. My name is Rob Parrish, and I'm head of simulations at QC Ware. Originally, that started as just simulations of chemical systems with quantum methods, but more recently, it's also come to encompass simulation of quantum circuits using high-performance classical techniques. And so I'm very excited to tell you today about some of our recent efforts to build a toolkit for high-performance classical simulations of quantum circuits, and to share with you a demo of what we've currently got implemented in the platform along those lines. These methods are invaluable for going and studying your current quantum algorithms and seeing how they perform on circuits with 20 to 30 qubits in them, being able to do hundreds of quantum circuit calls in a fast simulator. And so today I will share with you a few slides on the vision and API functionality that we have, and then a short demo on exactly what we've got implemented in the platform and what will be coming down the road in the next few months. So the very first thing we'll need within the Quasar and Vulkan quantum circuit simulator environment is a means to represent and manipulate quantum circuits. We provide that through a diagrammatic Python API where you can compose and build circuits that look like this or anything else that you might like, where we have the usual planar layout where we have the qubits on the rows and we have time along the columns. And every once in a while throughout the rows and columns, we encounter a quantum gate operation given here by either the boxes or these squiggly lines, this being a C0 gate here, this being an RY rotation. We also have the ability at the end of the circuit to have a measurement kernel where we can actually do the projective measurement process on the circuit here. And so the left plane of the screen here is the diagrammatic and manipulative API that we'll be seeing in a moment in Python. We then take that, and whether we're doing this on a CPU or a GPU, we go ahead and simulate in the 2 to the n dimensional configuration space of the state vector what actually happens within the circuit. So if it was a classical circuit, it would very much look like the following. You always start in the 0, 0, 0 state, and then every time you hit a classical gate, you would transition from one state of the RAM, the bits 0 or 1 in each one of the positions, to another. And you would do this deterministically throughout your algorithm. In quantum circuits, it's very much the same, except that all of the configurations can be active at one time. That looks something like this. In a quantum circuit, you always start in the 0, 0, 0 configuration, and then as you start applying gates, they can actually expand you so that you are in a non-zero linear combination of all 2 to the n of these configurations with a different amplitude on each one of these configurations. That's what we actually do in the simulation, is to store that full state vector and do linear algebra to apply each gate one at a time and be able to build up the full wave function psi here, which we can then at the very end, if you'd like, go ahead and measure, where we get a projective random measurement where we get stochastically or randomly a sequence of these different configurations each time we run and measure the circuit, with the probability of each one of these occurring being based on the square of this amplitude here. And that's actually what we do in the simulation process. Now, that's one operation you can have, is run a circuit and either return the state vector to the user or perform measurement. There are also higher order primitives that can be done with quantum circuits that we've built into the Quasar API. These include things like computing the expectation values of observables, operators like O, which might be specified in a sparse Pauli form, where the wave function psi is actually what the quantum circuit prepares. So that schematically looks like psi comes from a parameterized quantum circuit here, where the parameters are given by the colors of the RY gates in this particular case. And then some concept of a sparse Pauli operator that goes with this circuit that has different coefficients and then operators X, Y, or Z that act on one or more of the qubits at a time, and a whole bunch of these different clauses coming together. And if you have both of these concepts together, you can go ahead and either simulate or in real hardware go ahead and evaluate a complete scalar expectation value for this Pauli operator over this quantum wave function. And in particular, if you're doing that with classical simulation, that operation can be much faster than repeatedly building the state vector and doing a limited number of measurement operations on it if you know that you're trying to simulate an ideal quantum circuit that has been measured an infinite number of times. And so this is a technique where when we look at these higher order functions, we're able to get the simulation to run much faster and then to be able to study larger systems than we would otherwise be able to do and to get more traction into what we're doing with our quantum circuits. Diagonal expectation value is one such primitive. Another is the ability to compute a transition observable, where maybe the wave function in the bra and the ket are not the same. And there are techniques that we've developed to do that can be implemented within the Quasar and Vulkan stack. And a final and very interesting primitive that you can imagine that is actually very fast to simulate classically is the gradient of either a diagonal or transition observable with respect to the various parameters that occur in this quantum circuit gates here. So for instance, let's say I tweak this parameter up and down a little bit and ask how is the observable changing as a function of that angle. Well, that's the gradient element here that goes with that. And it turns out that there are classical techniques to do that extremely rapidly. It costs essentially a handful of state vector evaluations to extract the complete gradient where you see the perturbation for every single one of these separate angles at the end of your simulator. And so a combination of a really nice way to compose and build circuits with higher level primitives like this to be able to get simulations of things that aren't just the measurements at the outset of the kernel are definitely two of the most important characteristics of the Quasar environment. Now let me tell you what we actually have implemented in the Forge platform right now. We're slowly bringing over all of the Quasar and Vulkan pieces into this environment. First off, Quasar provides the ability to manipulate the circuits, something like this. You can build a circuit like this very quickly, as we'll see in our demo here in just a minute. And it has a full-fledged CPU-based API to do manipulations on your local computer of the following API functions. You can run state vectors, you can run measurements, you can run poly expectations, which is where you get the expectation value corresponding to every single poly operator in your linear combination of polys. You can get a poly expectation value, which is that final scalar expectation value that we were just talking about. And then you can also get the poly expectation value gradient, which is a key operation for optimizing variational quantum circuits. So all of these are present if you run Quasar in a local mode where you run it using the CPU resources of your current computer. We also have within the platform the ability to run at the moment a more limited set of capabilities where we go across the wire to a very powerful GPU and we run an optimized version of the code that exploits that GPU hardware to make the computational kernel much faster. And so for the moment there, we have this highly optimized GPU implementation of some Quasar API functions that are automatically deployed on a QC Ware hosted NVIDIA V100 device, which is much, much faster than the CPU code. And at the moment, we have the ability to run state vectors and measurement kernels with that. And we'll be moving the other API functions for poly expectation values and gradients and things like that, as well as providing some additional performance improvements in the GPU code within the coming weeks here. Okay, now we will have a brief demo of composing circuits using Forge and then simulating them using a mixture of the Quasar CPU backend as well as the Vulkan GPU backend for what capabilities are enabled for that. So the starting place, as usual, is forge.qcware.com, and we log in using whatever credentials we have. Mine are currently already in there. And while we're here on our API key, the very first tab that you encounter when you get into this, let's go ahead and copy our API key just because we'll need that later on in the demo to run the Vulkan functionality and consume QCT. We will now go ahead and go over to the Jupyter Notebooks section and actually spin that up and go into it and start using some Python 3 Jupyter notebooks to see what various functions we have to play with. And so the starting place for this is getting started. And then instead of just using the top level notebooks, we'll actually jump down into examples and then circuits. And there's a number of demo notebooks here that show you in some detail the details of how to build circuits, circuit composition, how to extract measurements from the end of them and understand the data type that's returned from that, how to compose poly operators that we can take expectation values of, and then how to take those expectation values and their derivatives in various notebooks here. For today's exercise, we're actually going to go ahead and build a new notebook. And so we're going to go over and grab a new Python 3 notebook here. And let's just go ahead and rename that. For me, that's the Control tab here. And we can then access the menu and rename it. In this case, this is going to be the CPU demo that we're going to be playing with here. And go over and actually start interacting with this notebook. So the first thing we're going to do here is go ahead and import Quasar. Quasar is an open source package that we develop at QC Ware. It's available on our public GitHub page, and it's a pure Python API to manipulate and do basic simulations of quantum circuits, including those higher order primitives that we talked about earlier, but to do them only on the CPU side. And so you're certainly welcome to take and download and use Quasar in your own environment outside of the Forge platform.
But be aware that the Vulkan GPU accelerated state vector simulator that works very nicely with Quasar is only present within the Forge stack here and can only be accessed at the moment by using the platform here. So we're going to go ahead and use, within this demo, only pure Quasar functionality. And so we're going to import Quasar. Python 3 only library, very fast import and very lightweight library to actually go ahead and start using. And the very first thing you'll surely want is to go ahead and build a circuit. And so that's just, you go in and say Quasar circuit, and you get an empty circuit. Go ahead and print it so we can actually see what an empty circuit looks like. And indeed, it has no qubit wires along the rows and no time indices along the columns, nothing there. So we have to start adding things to it, adding gates to it to make it more interesting. And that we can do by exploiting the fact that the circuit is a mutable object, and you can just go ahead and type a number of methods that circuit has that tell it how to add gates to itself. So in this case, we're going to add an RY gate, rotation around the y-axis on the Bloch sphere, and it needs first what qubit wire is it being applied to, qubit 0, and then how much do we rotate? That's a parameter that's optional, default to 0, and let's go ahead and call that theta 0.3 for now. Let's go ahead and print that circuit. Indeed, now we have one qubit wire, Q0, and one time index 0, with a single gate here in the middle that has that RY with a theta of 0.3 in it. We can go ahead and chain these operations to build a more interesting circuit. The one I'm going to be building today is called a CI single circuit. We'll see what it does to the state vector by simulating it. It's a very interesting operation. So the first thing we need to go and extend to a CI single circuit is to go ahead and add an RY gate on qubit wire 1. And let's go ahead and give that one a different theta. Let's make that one positive 0.2. I emphasize this is positive for reasons that you'll see here in a minute. And then we need a CZ gate, a two-body gate with no parameters in it. And that's going to run between qubit wire 0 and qubit wire 1. And then we're going to go ahead and run another RY gate also on qubit wire 1, but with the opposite angle of the one we just put in. So theta plus 0.2 here and theta minus 0.2 here. Then we're going to go ahead and finish this off with the CX gate that runs in the opposite direction from qubit wire 1 to qubit wire 0. And then we'll go ahead and print that circuit. And you see now we have a very interesting circuit that has now 3 RY gates, a CZ gate, and a CX gate. It occupies 2 qubit wires, and it has 4 time indices that go with it. We can delve a little bit deeper into this by using some properties of the circuit object. So for instance, we can ask the circuit, how many qubits do you have? 2, very simple. How many time indices do you have? 4. Not so bad. We can see some more interesting things though. For instance, one is some of these gates have parameters that go with them and some of them don't. Where are the parameters in them and in what order do they come out? Well, we can just ask circuit, give us your parameter string. This is a helper that basically makes a string that tells you where your parameters are in there. And so we can see that at these different time qubit indices, we have RY gates that each have a theta parameter that go like this, and we'll be able to reset those values and then also to take their derivatives if you look over in the derivatives notebook here. We can also go ahead and print out explicitly where the keys and gates within this circuit are. Let's go ahead and do that. Let's go for key gates in circuit gates items. This is a dictionary that actually contains a sorted set of these key gate pairs here. And we'll go ahead and print each of those out just so we can see what we have here. So print key gate. Oh, and I'm sorry, this should be key gate here. Okay, that's what we have there. Let's go ahead and do that. And we see, indeed, we have 5 gates in here. There's also a circuit.nGate argument or parameter that you can actually do. You'll see you have 5 gates. And they are lexically sorted by first the time index and then the qubit indices, with each of the keys being a tuple of what times and what qubits are active there. And we can now actually go, and if you looked at gate itself, gate is actually an object, and you can actually delve into it and see things like what unitary matrix does it represent and other properties of that particular gate. For instance, how to take its transpose or its adjoint and things of that nature. So the circuit object and the circuit composition is really no more difficult than this. This is very much the most basic way to build circuits up one gate at a time. You can also go into the circuit composition notebook, which I'll launch right here, and actually see how to do things like to concatenate multiple circuits together by joining in either time or in qubits. Also how to slice subsets out of this and how to do more types of things that can build you more advanced circuits in a quicker way. It's worth looking at that notebook to be able to figure that out. So again, that's Quasar Circuit Composition, which lives in the examples folder here right next to the demo that we're currently working on. So let's go back to the CPU demo here. And we're now ready at this point to actually go ahead and simulate this, this circuit and see what it actually produces as far as measurements and state vectors. Okay, let's go ahead and actually simulate the state vector. We're going to do this using CPU side code that's actually on the user's side. This is the Quasar quantum state vector simulator, and you just access it by actually building a backend object. It's called Quasar simulator backend. And let's go ahead and print that backend. That's just an object that helps you to go ahead and simulate these circuits in a way that you can't really tell what it is as far as what hardware it's using, so that you get the same types of responses, call and response arguments, regardless of what particular backend that you're using here. And so let's go ahead and use the backend to simulate the state vector. So state vector equals backend. If backend is a simulator, it may have a run state vector method. No hardware device is going to have this this method, obviously, but certain simulator-based backends will have it. And we just pass it the circuit and go ahead and run it. I'm going to go ahead and print that state vector, and we'll see what it does here for us. There it is. It does something very interesting. It has entries in the 0, 0, the 0, 1, and the 1, 0 state, but not in the 1, 1 state. That's what I mean by CI singles. It's only allowed, this circuit, no matter how many qubit wires you use it on, will only ever populate configurations that have a single on bit within them. So it's a very useful way to actually get data into a quantum circuit, whether that could represent a QML entity or to represent a, say, the beginning of a electronic structure computation for quantum chemistry. We can actually see that a little bit better. We can say Quasar format state vector. This is just a method that makes it easier to see what the state vector has in it, and it will tell you exactly which configurations go with which coefficients here, so you can get just a bit of a prettier printing using this particular sugar method that we have for you right here. Next, let's go ahead and pretend that we're not using a quantum state vector simulator, but we're actually using a quantum circuit device which produces measurements. So let's go ahead and say histogram equals backend run measurement. And so we still need to pass it, obviously, the circuit. We also need to pass it a number of measurements. Let's do 1,000 measurements here. Let's go ahead and print that histogram. Whoa, this is more interesting, because now we got there's no 1, 1 configurations, but we did get back 0, 0, 0, 1, and 1, 0 with some probabilistic outcome that came out here. And as you increase the number of measurements, that would converge to the squares of these amplitudes here. There's even a way to do that deterministically, which is why, in simulation, which is why we actually return probabilities here instead of the number of counts. And that is to go ahead and run this with an infinite number of measurements. You can do that by saying number of measurements none, and it will give you the true histogram in a limit of a very large number of ideal measurements of this quantum circuit that come out here. And so that's how to get measurements out of this particular object. Now, there are other things you can do. We discussed that observable expectation values and their gradients are very interesting primitives to use on near-term quantum circuit architectures. If you want to learn about that, the best thing to do is to go over to the Quasar Derivatives notebook, which walks you through the process of actually building up one of these poly operators. That's a sparse poly operator that you can take expectation values of, and then calculating the expectation value, the gradient thereof, and various other things that you can actually get using either ideal numbers of measurements or using actually a finite number of measurements and being able to get the pieces out for that. So this is all, again, to this point, using CPU-based code and actually using your own host computer to run that CPU-based code by using only Quasar primitives here. In the next example, we'll go a little bit further into getting state vectors and measurements off of the Vulkan backend piece of the code. So we're going to go ahead and actually build just a brand new notebook for this. If you want to see any more details of this, the Start Here notebook in the circuits actually has a good example of doing this. And so for this one, I'm going to go ahead and rename this new notebook we'll be playing with the demo on the GPU side. And again, we're going to just start with import Quasar. Let's go ahead and build what we're going to call a GHZ circuit. So this is the canonical circuit, the Bell state circuit, but it builds it for a much larger quantum computer up to an arbitrary number that we have to play with here. So let's in fact define a function for that. So let's say def GHZ, and let's take the number of qubits that we want to do that for. And so let's just go ahead and say circuit equals Quasar circuit. It always has a Hadamard gate on the 0th wire. And then let's go for k in range and qubit -1, and go ahead and add a CX gate to k plus 1, and then just return that circuit. So that's a nice little function that we can now use to go ahead and construct an arbitrary size GHZ circuit. So let's go ahead and build one for n qubit equals, let's start with 10 and just have a look at what that looks like. Great. So you can see you have many more gates than we've traditionally been using, and many more qubits and many more time indices then. So in this case, the 10 qubits are going to have a state vector dimension of 2 to the 10th, which is a bigger number than we've been playing with so far. We'll eventually raise that to near 30 qubits at the end of the demo today here, as we get through things here. So the first thing is to go ahead, and we're going to be using a different kind of backend now. It looks very similar to the Quasar backends, but now these are Forge backends that you're going to be using. You can actually find the definition of them here in the Getting Started notebook. So and the reason I do this is it's kind of a lengthy import call, and we have to get our API key configured before we can actually do anything there. So this is the call string here, and I'm going to bring that over and we'll actually see how that works in the GPU demo here. So let's go ahead and just copy that string in. This is my API key. You'll have to use your API key here. And then it's always a Quasar backend. It's just a question of whether it's classical simulator, classical Vulkan, whatever it may be as far as the backend, or you may be able to access hardware devices through these at different points in our API's history here. So there's that. And then we just, as we did before, we can go ahead and call. Let's start with state vector. It's going to be a backend run state vector. Always need to give it the circuit, and that's about it. And then we can print. Let's make sure we remember to use our Quasar format state vector method, because this is going to be a very sparse state vector that we get back here. So we should be able to do that and see indeed that we get a GHZ state with 1 over square root of 2 amplitude on the all 0 state and 1 over square root of 2 amplitude on the all 1 state. And we had to simulate a 2 to the n dimensional state vector to go ahead and do that. Obviously this is a toy example, but there may be many more interesting examples for even bigger qubit circuits that happen there. We also might want to do the histogram, and to run that with just run measurement. And let's pass the circuit in again. And then let's pass it the number of measurements. 1000, and let's print that histogram out again. And again, we got, in this case, statistically almost half and half on the all 0 and the all 1 state here with these 1000 measurements that we had here. Now what actually happened is this Quasar backend is the CPU side code. It's fairly efficient, but it is running over the cloud. So what actually will happen is when you go to, if I undo that, if you go to actually call the run state vector call here or the run measurement call here, the definition of your circuit and what you're trying to do with it gets sent to our servers, run on our servers, and then the result returned to you. And this can save a lot of time on your host side, especially for larger calculations, and especially when using a GPU-based simulator. So in a minute here, we're going to just change one line out, and we'll be running this thing on a GPU simulator and be able to handle much, much larger systems with this. So let's go ahead and do that. Okay, let's go ahead and run this on a GPU. So the only thing you have to do is, instead of classical simulator, classical really means CPU here, we have to use a Vulkan simulator here. Let's go ahead and do that. Then when you run your calls, they run this before, except that they're actually running under the hood through the wire on an NVIDIA V100 GPU, and they can run much faster, particularly for large-scale circuits that have more than about 20 qubits on them. Now, the one thing I would say is I do not recommend running state vector on more than about 20 qubits, simply because it's going to transmit that 2 to the n dimensional state vector over the wire. We can try it here with 20 qubits, much bigger circuit, and see if we can still get that to go. Whoops, I'm sorry. That's not runtime, that's just sitting there. And I don't know why my enter key here is not, there it is. It takes a lot longer, particularly because it's transmitting the state vector over the wire. And actually returning even all the non-zero elements that go with it. You can see that if you run measurement, it's obviously a much faster kernel for that kind of thing. And it's much faster than if you were running a CPU code for that. Let's go bigger. Let's go to 28 qubits, which is far too large, almost a gigabyte to transfer over the wire, but actually is quite fine when you go and run measurements, because the return measurement histogram is going to be a lot smaller. So let's first make sure we have the circuit built up for that. Much bigger circuit. Again, we're going to be using the Vulkan simulator there. Don't run state vector for this one, because usually you wouldn't need that anyways, and that state vector is going to be very large quantity, but this histogram measurement is going to be a very sparse object that's very easy to return over the cloud, and we should be able to get that back just like that, much faster than if we had run a CPU code for that. And so this is sort of the dream of where Quasar and Vulkan have gotten to, is that we should be able to run on 20 to 28, maybe closer to 30 on newer A100 hardware, state vector simulations, and be able to obtain these quantities over the wire without having any GPU local, and be able to obtain the quantities you really want.
With that, I'll say it's been a great pleasure to share with you some of our initial work on getting the Quasar and Vulkan high-performance quantum circuit simulation stack into Forge and into a form that you can use as a user. And I certainly hope to see some major performance improvements and extensions to the API specification over the coming months, which should make it that much more useful and valuable to industry researchers to try quantum circuit algorithms out. With that, I will turn the stage over to...
Hello. So the first question I would like to ask is, why quantum machine learning? So I think everyone understands now that classical machine learning is a set of very powerful tools that have found many applications, and they will continue to find even more applications in many sectors, like in the finance sector, in healthcare, in automotive, and so forth. So it only makes sense to ask whether quantum computing can actually help and enhance the power of classical machine learning and find even more applications in industrial level. So here's what we know so far. We know that if we had fault-tolerant quantum computers that would have access to classical data, then quantum machine learning can offer big advantages. We have developed many quantum algorithms recently in the field of machine learning that have been published in the main machine learning conferences, where we show exactly how such quantum computers can offer big advantages, whether it is in applications like recommendation systems, quantum clustering through our Q-means algorithm, training of neural networks, and so forth. All these algorithms use some extremely powerful but very subtle quantum tools that have to do, on one hand, with quantum linear algebra, things like multiplying matrices together, using quantum to solve linear system, for example, for support vector machines, but also things like faster expectation estimation, where we can use a smaller number of samples than in the classical case. So as I said, what we know is that universal fault-tolerant quantum computers can be extremely helpful. What we want to answer now is an even more important question, which is, can we bring this type of algorithms and this impact of quantum in machine learning closer to the NISQ era? And the answer is that we have concrete avenues to try and do that. First, by reducing the resource requirement of these quantum machine learning algorithms. It makes a very big difference taking a quantum algorithm that in theory may need 1 million qubits and figuring out a way of how to do the same thing using only 1,000 qubits. This really brings it much closer to the NISQ era. We can also propose, and this is what we're doing in collaboration with hardware partners, we can propose specific hardware architectures with the technology that exists today, but which are much more amenable to what we need them to do while applying a quantum machine learning algorithm. A third way of bringing quantum machine learning towards the NISQ era is by realizing that even classical machine learning has to deal and deals well with a lot of noise, whether this noise comes from the data or even when the noise is actually injected technically into the computation. So this is why we think that even noisy quantum machines could potentially offer advantages in quantum machine learning, because again, machine learning is an area where noise has to be dealt with, and we have ways of actually being able to do that. We can also propose NISQ quantum deep learning techniques based on quantum neural networks, but this time based on quantum neural networks where we can have probable guarantees about their efficiency and their accuracy. Our goal is to use the expertise and the experience and the intuition that we have from quantum algorithms in order to figure out the best architectures for things like quantum deep learning in a way that our intuition can drive us to the best architectures that can provide provable guarantees for their convergence and their accuracy. But this is not all. Quantum machine learning can offer not only efficiency and accuracy, but can also help providing machine learning applications where we care about things like interpretability and trust and energy savings. In order to provide NISQ variants of our quantum machine learning algorithms, the first thing we had to do was look under the hood and design a completely new engine. First, we had to deal with one of the biggest bottlenecks of quantum machine learning algorithm, which is how do we efficiently load classical data into quantum states. For us, this is extremely important because machine learning data is and will remain mostly classical. Internet data, images, texts, preferences, stocks, these are all classical data, and if we want quantum machine learning to really have an impact on machine learning, we need to be able to deal efficiently with classical data. So here's what we have done. We have devised optimal ways for loading classical data into quantum states with current hardware technology. We went one step further, and we have also proposed new hardware architectures based on the same technology that hardware manufacturers use today in order to enhance even more and make this procedure even more efficient. Here is an example. Imagine that your data points have 64 dimensions, meaning that you have 64 features of your data. We can load these classical data points into quantum states using 64 qubits and only logarithmic depth, meaning a depth of size 7. The number of total gates of your circuit is again 64. We can do more than that. We can actually find the optimal trade-offs between the number of qubits that one can use and the number of gates and depth of the circuit that one will use. So we can decrease a lot the number of qubits, and we can again load 64-dimensional data using only 16 qubits when we increase slightly the total number of gates to 72 from 64 and the circuit depth to 34. Of course, the power of our quantum data loaders is not only the fact that we can efficiently load classical data into quantum state, but we can actually use these quantum states to perform efficiently some of the core procedures that we need in classical machine learning. Such a core procedure is what we call distance estimation, where we estimate the similarity or the distance between different data points in order to be able to classify or to cluster them together. This is at the core of similarity learning, which provides accurate, efficient, and interpretable results in machine learning. What we have done is that we have used our quantum data loaders in order to provide the optimal distance estimation procedures with current quantum hardware. This allows us, again, to provide NISQ variants of our quantum machine learning algorithms. And here is an example where we can implement the distance estimation procedure between two data points that each one of them has 16 dimensions with a quantum circuit that uses 16 qubits and a number of gates of 35, while the depth of the circuit is only 13 because it grows logarithmically on the dimension of the points.
We're now ready to demo our quantum machine learning functionalities. We open our Jupyter notebooks. Within examples, we find machine learning, and within there, the QML notebook. The QML notebook starts with a discussion on why QML and how we do what we do. Under the hood, we find our quantum language Quasar, our data loaders, and our distance estimation procedures. We also provide some simple dataset and visualization functionalities so that we are ready to start our quantum machine learning applications. The first application that we will look at is in supervised learning, and more precisely in classification. We will use our first classifier, the quantum nearest centroid, and what we will do is that we will first generate some classical data, and then we will use the fit and predict function with a model Q nearest centroid. Let's run the code. Here we can see the quantum labels, the classical labels, and a visualization of the results that shows that quantum classification works very well. Now we will demo our quantum nearest neighbors classifier. Again, we will use the same function fit and predict once we generate some data, and now our model will be the Q neighbors classifier. We can run it. And once again, we get the quantum labels, the classical labels, and we can benchmark the two techniques and see that the quantum classification works very well. Now we're going to demo quantum regression. We're going to use our quantum neighbors regressor. We again produce some synthetic data, and we run our fit and predict function with a model Q neighbors regressor. Let's run the code. We see that we can get very good results, very similar to the classical case, where we benchmarked our Q neighbors regressor with the classical K neighbors regressor from scikit-learn. We're now going to demo our unsupervised learning functionalities, and in particular, we will look at Q-means, our quantum algorithm for clustering. Here, again, we generate some data clusters, and we use the fit and predict function with the model Q-means. We can run the code. And we see again how the quantum algorithm has clustered the points together and how the classical one has clustered the points together. And we can see that while the clusters are not the same, the quantum clustering provides very good results.
Hello, welcome to the optimization part of today's demonstration. My name is Wim van Den, and I'm the head Quantum Algorithms US of QC Ware. I'll be showing you some of the features that we've built into Forge that should help you solve optimization problems better using quantum computers. Okay, let's get started. Quantum optimization can happen in many different ways. And today what I'll be showing you are two cases, quantum annealing and the QAOA approach, where on our platform we've got ways of kind of improving over the standard approach. First, I'll talk about anneal offsets. This is a technique that has been developed in part by two people who work at QC Ware, and the details are available in a technical article online. But I'll be going over just the general picture today, and I'll give you a demonstration using our platform. Now, the problem potentially with quantum annealing is that some parts of the system reach their minimum energy state before other parts. And when that happens, you can have a misalignment of the final whole state where you reach only a local minimum and not a global minimum. And what is really kind of the cause of this problem is that the annealing happens in an asynchronous manner, that some parts move faster than other parts for one reason or the other. Now, the idea of offset annealing is that you can kind of anticipate this problem and you can adjust for it. You can reschedule your annealing procedure in such a way that the reaching of the ground state is happening in a synchronous manner, and thereby avoiding this problem of getting stuck in a local but not a global minimum. Okay, so let's do anneal offsets on our Forge platform. We have the usual installation of the packages, and we define the problem instance, the alternating sectors chain problem, which has the property that this asynchronous issue comes up quite likely. We define this for 40 qubits, 40 spins, and we define our anneal offsets procedure, which is a parameter delta that tells us how strongly or weakly to apply anneal offsets.
So first, we're going to do it without. We set delta to 0 and we execute it. So that's what's going on live now. We're running our algorithm without anneal offsets on the quantum hardware of the D-Wave annealer. And in a few seconds, we see that the success probability of the standard approach is 30%. Now we're going to run it again, but now we're going to turn on the anneal offsets idea with a parameter of 0.02. Now this is a probabilistic algorithm, so when you execute it, you might see different outcomes, but this should convey kind of the general idea of this approach. And we're almost there, and there we are, 50%. So what used to be a 30% success probability now has become a 50% probability, which is quite significant, and hopefully gets more significant as the problem instances get bigger and bigger. The end. Okay, now let's look at a quantum circuit approach to solving optimization problems. Specifically, we're going to look at the QAOA approach and the issue of for which angles QAOA works the best. Now, as a reminder, QAOA is an approach where you use a sequence of layers, and after you execute these layers, you hope that you found the best possible solution. And each layer is controlled by two parameters, beta and gamma, two angles. And depending upon these angles, your QAOA will perform good, or maybe not so good, or maybe excellent. And finding these angles is a big and important part of getting your QAOA approach to work as best as is possible. Now, finding these angles is not so easy, because even when you have a layer depth 1, in other words, you've got two angles, it can be very sensitive. So on the right, we've got a plot. This is a problem that involves less than 20 qubits. And you can see that as you vary your beta and your gamma parameters, the algorithm will have a good expectation, the blue color, or it will have a not so good expectation, the red colors. And figuring out which angles are going to do, the best possible job for your algorithm is an important task, and it's not obvious because this pattern is very intricate, and finding where the bluest of the blue values are is tricky to do and can be very expensive. So fortunately at QC Ware we developed some techniques that help you in finding those best angles. We have a procedure called Find Optimal QAOA Angles, and this is explained in the notebook and again in documentation. So again, you can go on our platform and explore this procedure. But let's just give a small demonstration to see how it works in practice. Okay, let's find the optimal angles for QAOA on a simple 4-qubit problem. We do the usual import. We define our problem using a Q matrix. Here it is the expression for it. And now we're going to run our code and see what angles QAOA should use to get the best possible expectation. So we're doing this live, and the code is running, and there's the optimal expectation, almost -10, and the angles are as follows, 2.65 and 0.1. Now, how difficult was that? Well, let's create a map of the expectation. And this is a very complicated map, and we really went through this very quickly and found where the white dot is right there, that those are the best angles. Now, what is kind of remarkable about our code is that it can be run on extremely large instances for QAOA. Here we're creating a problem instance of 100 spins. Now, you can clearly not simulate that, but nevertheless, our algorithm can find the right angles relatively quickly and actually can produce the map that goes with it also relatively quickly. We're doing this right now live, and soon you'll see that the map looks very different from the previous map. This is a large problem, 100 spins, but the map looks very regular. And that's kind of an interesting thing when you run your QAOA approach. And so this code that we have here really should help you in understanding when to apply QAOA and when not, and how to best use the angles to get your best expectation. Okay, I hope you enjoyed this demonstration, and we'll now continue with our webinar.
Thank you everybody for going into more details into your respective areas. Forge is an enterprise product for researchers in academia, government, and industry. We have several pricing tiers, like simple pay-as-you-go plans, or small, medium, and large enterprise tiers. With these plans, you buy subscriptions that allow you to use a certain amount of quantum computing time, or QCT, during your subscription period. And let's go into questions.